Juno will use remote sensing to inspect Jupiter from its innermost core to the outer reaches of the magnetic bubble the giant planet inhabits. Juno will be the first probe to visit the regions above the poles of Jupiter, witnessing energies in the magnetosphere that create its extraordinary ultraviolet auroras. There are many theories about the origins of Jupiter. Here's what we think happened. Nearly 5 billion years ago, a star in our galaxy exploded. The explosion caused a nearby cloud of gas and dust to collapse and flatten into a spinning disk. Most of the gas and dust collected into a hot, dense core that became our Sun. The remaining debris formed the planets and other small bodies in our solar system. And the majority of that debris came together to form the giant planet, Jupiter. Of all the 8 planets, we believe Jupiter formed first. Understanding the formation of Jupiter is essential to understanding the origins of our entire solar system, the formation of Earth, and the most basic foundations of life as we know it. Jupiter is 1,300 times the volume of Earth, more than twice the mass of all the other planets combined, the 5th planet from the Sun, and the largest planet in our solar system. Because of its enormous size and powerful gravity, it is believed that Jupiter has influenced the formation and evolution of the other bodies that orbit our Sun. Unlike Earth and the other smaller planets, the composition of Jupiter has remained unchanged since the solar system began. Like a time capsule, Jupiter can help us reconstruct nearly 5 billion years of history. Mission Juno will help prove or disprove theories about the types and amounts of materials that contribute to the composition of Jupiter. By peering beneath its clouds and discovering what Jupiter is truly like, Juno will also test our ideas about the formation of planets, as well as other major secrets of our solar system. Measuring the amount of water in Jupiter will help us understand how and where in our solar system the giant planet formed. Mapping the gravity and magnetic fields of Jupiter teaches us about the planet's hidden interior and whether it has a solid core. In our quest to unlock the history of the planets, Jupiter is the gateway, and Juno holds the key.
This is my transmitter. Maybe it's something you can use, I don't know.
The High Juno experiment is something that a group of us came up with.
The biggest challenge we had was we didn't know if this was going to work or not.
If it works, I'm part of history.
This is W6JPL, Jet Propulsion Laboratory in Pasadena, California. Hello, CQ, CQ, CQ.
The Earth flyby is Juno's way of gaining some extra speed and changing direction so that its orbit can take it to Jupiter.
We said, what if we actually sent something to Juno? Basically came up with the idea that we could send Morse code to Juno, enlist the support of amateur radio operators around the world.
So the intent is to join amateur radio community together in a coordinated transmission from Earth to the Juno spacecraft as it flies by.
The website would tell them, okay, key down now, then key up, transmit for 30 seconds. And that's how we would send a DIT. Everybody knows Morse code is dit, 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 da, da. Well, it turns out to say hi to Juno, it takes 4 DITs, in space, and then 2 DITs for the eye.
I thought, wow, that's a neat thing to do, and they're going to need a lot of people to pull this thing off. I said, I'm good to go.
We're getting ready right now. Here we go.
And now we are transmitting here.
They could hear ham radio operators all over the world doing this, which was really remarkable.
Everybody's doing this at the same time. Thousands and thousands of hams.
With any luck, the Juno spacecraft will be able to listen and hear all these amateur radio transmissions.
And so what we're doing now is we're looking at the data that's come down to see if we can put together that signal that says, hi.
Will it work? Who knows?
I have the audio from Juno. I'd love you to listen to it.
This is it.
This sounds very cool.
Actually worked and it heard us.
When you think about what it is, it was really, really amazing.
How many times do you get to say hi to a spacecraft that's flying by your planet?
To be a part of it, that was very great.
More than thinking about what it means to me, I think it's just such a great thing that humankind has the ability to think beyond our own environment. It's the curiosity, it's the adventuring spirit, I think, the space program has given us.
Hi, Juno!
Hi, Juno!
Hi, Juno!
Hi, Juno!
Hi, Juno!
Hi, Juno. Goodbye, thank you.
Okay, take 17.
Hundreds of scientists and engineers in 5 countries have been working for more than 10 years to design and build the Juno spacecraft. This solar-powered probe will travel 400 million miles into space with instruments uniquely built to withstand deadly radiation and the fiercely cold environment of Jupiter. Juno will conduct an unprecedented examination of the atmosphere, the interior, and the vast magnetic field of the giant planet.
I've been asked in to help with the gravity science experiment. Measuring Jupiter's gravity depends on measuring changes in the spacecraft velocities that goes around Jupiter. What we're looking at is for variations in that acceleration rate that tells us something about the change in the gravitational field of Jupiter as it gets closer to the surface associated with a mass structure inside. And so what we're trying to do then is measure the spacecraft's velocity as a function of time very, very accurately. And we do that by measuring the Doppler shift of the radio signal. So if you've ever heard a fire engine going by with its siren, as it's approaching you, it's high pitch, and when it goes by, it goes, right? That Doppler shift, that change in pitch, tells you about the velocity of the fire engine relative to you. So the instrument that we use is sort of a combination of the listening on the ground to the radio signal and the radio signal transmitted by the spacecraft. So the biggest part of the instrument, of course, is a 34-meter diameter radio antenna at Goldstone, California. Then on the spacecraft, there's a high-gain antenna that's pointed at the Earth. So the radio instrument measures the voltage coming in from the antenna from the Earth, and then it transmits a voltage that goes fed out to the radio signal to send back to the Earth. And then the gravity measurement tells us something about density variations, which then can tell us something about whether there's storms on the outside or whether they penetrate all the way through, and whether there's some hint of a structure at the center other than just compressed gas of the hydrogen.
JADE, the Jovian Auroral Dynamics Experiment, is a set of instruments that measures the electrons and ions. Those are particles, very tiny charged particles that are parts of an atom. And those particles actually produce the aurora. They follow along the magnetic field lines and they come down into the atmosphere of Jupiter, and they excite different sorts of interactions that emit light, different wavelengths of light. Those we observe as the aurora, but the aurora is really caused by these tiny, tiny particles coming down into the atmosphere. And JADE actually measures those individual particles. There are 3 identical electron sensors, and they look off in 3 different directions around the belly band of the spacecraft, so that they've got a broad field of view, 120 degrees wide, so the 3 of them actually can see all the way around the spacecraft all the time. The JADE ion instrument is different. It actually has a thing that looks a little bit more like a hamster wheel and a hamster cage, and that's to allow particles to come in over 270 degrees of observing angle, and twice per minute the Juno spacecraft spins around, and that allows that field of view to observe all of space. And so we're trying to understand what's the same and different between our own aurora and the aurora of Jupiter so that we can understand the processes really in detail for the first time. We'll be fully successful when we can come back and tell the world how it really works, what particles are involved, and why.
It's the Jupiter Energetic Particle Detector Instrument, and the acronym does not quite work out properly, but somebody loved the word Jedi for obvious reasons. We affectionately call our instrument the hockey puck because the main sensor is about the size and shape of a hockey puck disc. That hockey puck is sort of glued on or attached to a box which holds all the electronics associated with the sensor. JADE in particular works in very close coordination with JEDI. So JADE is measuring the lower energy part of the charged particles that are in Jupiter's environment. JEDI measures the higher energy particles. Those particles then go through the instrument and strike what's called a microchannel plate sensor. And a microchannel plate sensor amplifies the signal so that you get a current out the back end, and modern electronics can measure electric currents. We measure the radiation belts around planets. All the strongly magnetized planets have radiation belts. Jupiter has the most intense and interesting radiation belts. It's a rotationally dominated space environment or magnetosphere, where Earth is a solar wind-driven space environment. By studying 2 different environments that are powered by different things, you can begin to isolate the physical processes that are causing these variations. We hope to make great discoveries there.
A Jupiter infrared auroral mapper is an image spectrometer. At the beginning, it was meant for supporting auroral observations, to make images of aurora, and at the same time to look at the different view of the aurora. GRAM is made of two pieces. One part of GRAM is called the optical head, where is the sensitive part of the instrument that can focus the images, like a camera. And there is another box, which is the main electronic. And we can take images in two different wavelengths. One is devoted to the auroral observations, and the other part of the detector, the imager, it's sensitive to the thermal emission of the planet. So at the same time, we can take these two pictures that are superimposed, one above the other one, for observing the aurora if it's present. The reason why we are not with all the other instruments, but we are on a side in the aft deck of the spacecraft, is because we entered the mission later. So there was no more room in the big place, in the place where all the other instruments are. So we had to run quite fast to keep the pace with the mission.
JunoCam is on the spacecraft to take pictures of Jupiter, and we specifically designed it to get pictures of the polar regions of Jupiter. We've had a number of spacecraft that have flown past Jupiter and taken pictures, taken movies, but they've always been in the equatorial plane. And so this mission is the first one that we really get up over the polar regions. Let me mention that all of our pictures are of the cloud tops. Jupiter is a ball of gas, and all we will see are clouds. But they're very interesting, very dynamic clouds, so it should be fun. JunoCam is a unique element of the payload on this spacecraft because from the outset, its reason for being on the payload was to do outreach to the public. We do not have enough data volume to take a picture on every spin. We are going to have to be choosy and select what are the places that we want to take pictures of. We are going to invite the amateur astronomy community to send us their best data. So approximately a month away from when we take our data, we will be collecting the pictures from the amateur astronomy community and talk about why they would take a picture in any given latitude. And so the whole theme is to do science in a fishbowl. Let's do what we would do, but let's do it in a public forum so that the public can participate. And I'll be very happy if everybody gets involved the way I hope they do.
Years ago, the magnetic field provided a reference for navigation on Earth. So for 400 or 500 years, whenever ships crossed the ocean, they carried compasses so they could find their way when you can't see stars or landmass. Magnetometer is like a fancy compass. It measures both the direction and the magnitude of the magnetic field. So in this case, we fly a magnetic sensor at the very outer extremity of the spacecraft. We're on what's called a magnetometer boom, which is about 12 feet in length. It's about twice as long as I am tall. The primary purpose for our investigation is to map the magnetic field of Jupiter very accurately and try to understand how it's generated deep down inside Jupiter, in Jupiter's electrically conducting core. What we're going to do is make very, very accurate measurements in orbit about Jupiter and basically envelop Jupiter in a dense net of observations. And that'll give us the ability to image what the magnetic field looks like down in Jupiter's core where it's generated.
NASA loves acronyms, and so I just simply abbreviated microwave radiometer as MWR. From its name, it measures the radiation in the microwave region. Now that sounds like, a lot of highfalutin scientific terms, but it's really pretty simple. What we're actually doing is measuring the thermal radiation from the atmosphere of Jupiter beneath the clouds. And at every wavelength, we have 6 wavelengths on the instrument. Every wavelength is designed to look at a different region of the atmosphere, measure the thermal radiation coming up from some different region in the atmosphere. And by measuring them with the spacecraft, we'll be able to put that together into a picture, a 3-dimensional picture of the atmospheric structure of Jupiter. What we've come up with as the most effective way to build an antenna is a big flat array that's about 5 feet square all the way around. It's as big as the side of a spacecraft, which is not a coincidence because we sort of sized the spacecraft to hold an antenna for our longest wavelength. Now, the other wavelengths are progressively smaller by factors of 2 at every step. So it turns out another side of the spacecraft can hold all of the rest. So we have no idea what we're going to see because nobody's ever seen this region before. It's going to be a surprise to all of us when we get the information back. So we expect to discover all sorts of new things.
UVS stands for ultraviolet spectrograph. It's an instrument that looks at ultraviolet light you can't see with your eyes. It's too short a wavelength, but it also breaks that light up into different colors, much like a prism would break up white light into a rainbow. It has 2 components to it, actually. One is the sensor, which is sort of a telescope plus a spectrograph side by side. And all the electronics, except what need to be right at the sensor, are put in another box, which is deep inside a vault, which on Juno protects all the sensitive electronics from the radiation at Jupiter. Jupiter has some similarity to Earth. The Earth has northern lights, auroras, and they're spectacular to watch. Jupiter's auroras are like 1,000 times bigger. So the auroral oval on Jupiter is bigger than the entire Earth and much, much more powerful. And it's always on, but it's much easier to look at it in ultraviolet wavelengths because we can see it on the day side as well. When we see light from those different colors in the UV, they tell us different things about Jupiter's upper atmosphere and the particles that are causing the auroras to happen. We'll be able to contrast how auroras work at Earth with how they work at Jupiter. And there are many differences we already know, but there's a lot of things we've never been able to see at Jupiter that we can see with Juno once we get there.
The WAVES instrument is basically a radio. It tunes to frequencies all the way from 50 hertz, which is near the bottom of the audio frequency range, up to above 40 megahertz, which is above the limit of the radio emissions that Jupiter generates. The WAVES instrument has 2 sensors. One is designed to measure the electric field component of these waves, and it looks like a pair of rabbit ear antennas that you might have had on a TV when you were a kid, except these are about 10 feet long. The other sensor is a much smaller device. It's about 10 inches long, and it's basically a coil of wire. It has about 10,000 turns on it, and it's designed to measure the magnetic fluctuations of waves. So these 2 sensors are used by the receivers to study the various phenomenon, particularly in Jupiter's polar magnetosphere. For example, the maximum frequency of the radio emissions that we detect told us what the magnetic field strength was in the magnetosphere of Jupiter, long before any spacecraft arrived. Juno was designed to actually go to another planet and make the first measurements of an extraterrestrial auroral region in great detail. So I think we learn about ourselves by studying other environments in the universe.
After 5 years of being alone in space, Juno approaches Jupiter and begins reaching a top speed of 160,000 miles per hour, officially becoming the fastest man-made object in history. The main engine ignites to slow down the spacecraft, and Juno is captured by the powerful gravitational pull of Jupiter. Settling into the most challenging orbit ever attempted, Juno will come as close as 3,100 miles to the planet's cloud tops. Juno will continually duck below deadly radiation belts as it studies Jupiter in unprecedented detail for more than a year. After orbiting Jupiter for over a year, the Juno craft will dive deep into the atmosphere and burn up. But the mission will never truly end. No matter how many answers we find, there will always be more questions. Our search for understanding and meaning continues.